Hello, welcome to my channel and to my first video in Android Reverse Engineering Basics playlist. I'm an active reverse engineer and I'd like to share with you my knowledge and experience. This video and channel will be helpful for everybody who is curious about how Android works under the hood. In this first video, I will explain you how Android applications are compiled, packaged and organized. Apps are typically written in Java or Kotlin in Android Studio. Frameworks like Flutter or React Native may be used, but ultimately the core logic of app is compiled into a Java-compatible bytecode. Java source files with .java extension are compiled into a Java bytecode, files with .class extension by the Java compiler, javac. Kotlin source files with .kt extension are compiled by the Kotlin compiler, Kotlin C, into files with .class as well, and they are fully compatible with the Java Virtual Machine, JVM. However, Android does not run on the JVM. This bytecode needs further transformation by Android-specific tools. All files with .class extension are processed by DX on older Android versions and D8 on newer Android versions, DEXer tools, to produce one or more Dalvik Executable DEX files. DEX files are optimized for execution on DVM, Dalvik Virtual Machine, which was used until Android 4.4, and IRT, Android Runtime, which was introduced in Android 4.4 and fully adopted in Android 5.0 for better performance. During the conversion of files to DEX, the compiler applies optimizations like replacing small methods with their code, evaluating constants at compile time, and removing unreachable code. DEX files, compiled resources like XML layouts, strings and so on, and assets like images or raw files are bundled together using Android Asset Packaging Tool, AAPT or AAPT2. This process produces an APK, Android Package or AAB, Android App Bundle, depending on the project's configuration. An APK is essentially a zip archive optimized for Android. If you change the .apk extension to .zip, you will be able to open it and inspect using any archive manager, and you will be able to see the app's code, resources, signatures, and so on. The APK is a final installation file that is installed and executed on Android device. It contains everything needed for the app to run. An AAB is a distribution format designed specifically for Google Play and isn't installed on the user's device directly. Instead, the Play Store processes AAB and dynamically generates APK file depending on each device configuration. This means that Play Store delivers only resources relevant for the user's device. For example, the correct CPU architecture, screen density, and language specs. This approach minimizes app's size and improves efficiency. So if the user downloads the application from Google Play, they are actually downloading a customized APK file generated from AAB. App bundles are mandatory for Play Store submissions, but outside of Play Market, APKs are still the primary distribution format. Now, let's look on the structure of Android APK. Inside an APK you will find AndroidManifest.xml, which defines permissions, app components, and essential configurations. Classes.dex, where the compiled Dalvik bytecode logic lives, and that's the actual logic of the app. Res package, which contains compiled resources like layouts, strings, images in a XML format. Assets folder, which holds raw files, which app can access during the runtime. Lib folder, where native libraries with .so extension live for different CPU architecture. And finally META-INF, which contains cryptographic signatures and certificates to ensure APK's integrity. When we start reverse engineering, that's usually the entry point. We unpack the APK, explore the resources, assets, and locates its code. The manifest is the brain of application. It defines the app's package name, version, and entry points, like activities and services. Permissions required by the app, like camera or internet access, and hardware features required by the application. The manifest is stored in binary XML format in the APK, but different tools can convert it to a human-readable XML file. When reverse engineering the application, the manifest is one of the first things to be checked, since it reveals the app's structure and the app's entry points, which is usually the first thing to be checked during static analysis of the code. Inside the APK, the classes.dex file holds all the compiled app's logic. Dex stands for Dalvik Executable, which is a special format optimized for Android. Unlike the JVM, which is stack-based, Dalvik and IRT are register-based, meaning that they hold values in a fixed register instead of popping and pushing values from the stack. This makes Android apps run more efficiently on low-memory devices. Big applications may have several DEX files like classes2.dex, classes3.dex, and so on. And tools like JDEX and dex2jar let us convert DEX files to a readable Java code for analysis. Now that we understand what's inside DEX files, let's take a step deeper. While DEX files show us compiled apps logic, it's not something you can easily read or modify. That's where Smali comes in. Smali is a human-readable assembly language which represents Dalvik bytecode found in DEX files. It is a low-level language that maps almost one-to-one all the instructions executed by Android Runtime or Dalvik virtual machine. The names Smali and Backsmali come from the names of tools themselves. Backsmali disassembles DEX files into a Smali code, and Smali reassembles Smali code back to the DEX files. Now on the screen you may see how a simple Java code would be represented in a Smali code. In this example, the methods v1 and v2 holds the method's arguments, and v0 holds the result. Instructions like add int correspond directly to the Dalvik bytecode operations. Smali gives you a full control over bytecode instructions and operations, making it essential for analyzing obfuscated code when Java decompilers fail, performing precise low-level modifications that could not be done from the Java side, and debugging bugs which appear only on a bytecode level or working with a heavily optimized bytecode. However, in real-world scenarios, you will not need to work with Smali directly. Modern tools like JDEX can decompile majority of APKs back to Java code, and Smali editing is reserved for more advanced reverse engineering or patching tasks. The REST directory contains all compiled application resources like strings, images, layouts, and so on. Reverse engineers often inspect resources to find hidden strings or to understand the UI flow. Most XML files in this directory are compiled into a binary XML, which can be easily decompiled using different tools like APK tool. The assets folder contains raw files which can be read by the application during runtime. This folder contains configuration files, scripts, or even embedded data. Unlike resources, these files are not compiled or processed. They are stored the same as the developer puts them. This makes assets folder a real goldmine for reverse engineers, since it may contain API keys, text files, or even entire mini programs written in a plain text. The lib directory contains compiled libraries for different CPU architectures like ARM or x86. These are .so shared object files, written usually in a C or C++ languages for a performance-critical tasks like encryption or game engines. However, some developers may hide malicious logic there to make it harder to access and read it. Reverse engineering native libraries is a more advanced task since it requires tools like IDA Pro or Ghidra and requires understanding of assembly code. Finally, META-INF contains signature information. APKs are digitally signed so that Android can verify they haven't been tampered with. If you modify and reassign APK, this folder changes. It is important to understand that because it can help to troubleshoot issues when installing the patched APK. So that's it. We have walked through the Android compilation process and explored the APK in details, including DEX files and Smali code. This foundation will help us in future when we will start decompiling APKs, reading Smali code, and modifying applications. If this video was helpful for you, please like and subscribe. This helps me to understand that this content is valuable. Thanks for watching.